Continuing our discussion on weak interactions, we discussed the fact that weak interactions violate parity, they also violate charge conjugation symmetry, and the combined symmetry of charge conjugation and parity is conserved in most of the weak interactions. Now, let us look at it a little in a little more details. Let us look at the parity of quantum number, how we can assign the parity in to the wave functions. Quantum mechanically, wave function, let us say r theta phi, let us consider the case where this can be separated into the radial part and the angular parts. The angular part is called the spherical harmonics, like in the case of hydrogen atom. What does parity do to this? R theta phi, the polar coordinates under parity goes to r pi minus theta and pi plus phi. How do we see that? Let us look at the theta. R is just the magnitude of the position vector, which remains the same whether it is in one direction or opposite to that. Therefore, parity will not do anything on that, that is a scalar quantity. Now, theta, let us take the y z plane and consider the position vector lying in that. In that case, this is your theta, the polar angle, and under parity it will go to minus r, and this angle is now theta. And what is the polar angle of minus r? It is the angle measured from z axis, which is pi minus theta. It is clear. So, under parity theta goes to pi minus theta. For the case of azimuthal angle, let us go to the x y plane. So, it is the x y plane. In the x y plane, projection of the position vector, let me call that rho, which is equal to r sin theta cos phi x plus sin phi y, as you know. Let us say it makes an angle in this particular situation a phi with the x axis. Under parity, it will go to the opposite direction with phi here. And what is the angle that minus rho makes with x axis? It is pi plus phi. So, that is what you have here. And what about y l m theta phi? How does it go to what does it go into under parity? Just note that this is proportional to Legendre polynomial, associated Legendre polynomial as a function of cos theta times exponential I m phi. These are the phi and theta dependence of the spherical polar coordinates, spherical harmonics y l m, and the azimuthal angle under parity goes to pi plus phi, and e power I m phi will go to e power I m phi plus pi under parity, of course, which is equal to e power I m, okay, let me write it as I pi m e power I m phi, which is equal to minus 1, e power I pi is minus 1 power m e power I m phi. So, there is a factor of minus 1 power m that the e power I m factor, I m phi factor picks up, or the azimuthal part of the wave function picks up. What about the polar angle part? Under parity, it will go to P L m with cos theta cosine of pi minus theta now, and without going into analyzing it, we will just give you the result. It is equal to minus 1 power L plus m. You have to just look at how the Legendre, associated Legendre polynomials behave under theta going to pi minus theta. P L m cos theta, and together y L m theta phi under parity goes to y L m pi minus theta pi plus phi is equal to minus 1 power L plus m, L plus 2 m, minus 1 power 2 m is always positive. So, we do not have to worry about it. So, it is minus 1 power L y L m theta phi. So, this factor decides whether the total wave function is even under parity or odd under parity. If it is even under parity, maybe if L is odd, then it is an odd function of parity, function under parity. If it is even, if L is even, then it is even under parity. Now, assumption to start with, that strong interactions and electromagnetic interactions conserve parity. This need to be checked experimentally, and experimentally we have not seen any violation, parity violation in strong interaction or electromagnetic interaction. But for this, we need to assign intrinsic parities to various different particles. Okay. When you talk about intrinsic parity, we do not have any wave function like this that we can, and orbital angular momentum that we can think about. A particle is a particle which has maximally, which can have a spin for this thing. So, without going into how exactly that comes about, there is the question that we will ask is, looking at various different reactions, is it possible to assign intrinsic parities to particles, different particles consistently, so that the strong interactions and electromagnetic interactions conserve parity? Answer is yes, this can be done consistently. So, what we have to do is to say psi, the particle wave function, how does it undergo, how does it change under parity? It can either pick up a plus sign or a minus sign. Okay. So, this is called even parity and this is the odd parity. So, even and odd parity for these particles can be assigned consistently. So, how do we do that convention? To start with, spin half particles like proton, neutron, electron, muon, etc., neutrinos, etc., all have positive parity. Antiparticles spin half like antiproton, antineutron, positron, mu plus, etc., have negative parity, or I can write as even parity and odd parity. Other particles so consistently considering reactions. For example, pions, pi plus, pi minus, and pi 0, all have odd parity. We will not go into how one determines this or how one actually assigns this. There is a consistent way of doing it. This has been done, and now let us look at one particular reaction. Observation of K0 decay. It was observed that it could decay into 2 pions, pi zeros or pi plus plus. It actually mostly decays into this, but there was a small part of this decaying into pi plus, pi minus, pi 0, something like 1 in 10 power minus 7. Decays to 3 pions. Now, if pion has odd parity, parity minus 1, the final state of the first reaction decay gives together parity plus minus into minus. The second reaction it is minus into minus into minus 3 times, and that 4 together it is minus 1. So, the K0 decays to final stage with positive parity mostly, but also there is a small decay probability for it to decay into negative parity final state, which in other ways says that K0 is a particle which cannot be assigned a proper parity to this one, or the other way to interpret it is that parity is not conserved in such decays. It can decay into positive or negative parities. There was also an observation of similar other particle K plus going into pi plus pi 0 or going into pi plus pi minus pi plus, 3 pions or 2 pions. Again, one final state is even parity, the other one is odd parity. In fact, historically speaking, initially these particles were thought of to be 2 different particles because parity was violated in the final state, or they decay into 2 different final states with 2 different parities. But then it was suggested by T. D. Lee and C. N. Yang that parity is actually parity could be thought of violated in weak decays like this, and then further on it was experimentally found, as we saw earlier, that parity is indeed violated in CP violation, and this fetched Nobel Prize for Lee and Yang in 1957. Combined CP violation is also observed in the weak decays, weak interactions. So, for example, if you consider again K meson system and more recently B meson system. Both of these show CP violation. There are dedicated experiments, there had been dedicated experiments running for a long time, many decades, investigating the CP violation in the K meson system. Experiments, accelerators were tuned to electron positron colliders, for example, could be tuned to energies which will abundantly produce K mesons, different excited states of K mesons also. And similarly, one could tune these collider energies to B meson masses, and you can produce these mesons abundantly. They will decay into different channels. Looking at their decay properties, decay channels, one can study the CP properties, and then it has been found that CP violation is a feature of K meson system and B meson system. CP violation, unlike the parity violation, is somewhat smaller. When I say smaller, what I mean is the following. Consider the case of beta decay. In beta decay, electrons coming out are always observed to be left-handed. There is no right-handed lepton which is coming, which is observed in the beta decay. Whereas parity conservation or parity transformation would take left-handed electron to right-handed electron. So, if parity was a good symmetry, or if things were symmetric under parity, then equal number of these two left-handed and right-handed electrons would have been there in beta decay. So, non-observation of right-handed electrons or left-handed positrons in beta decay says that parity is violated and maximally, that is, there is no left-handed right-handed electron at all observed. But in the case of CP violation, when we consider two processes, one of which can be the CP transformed state of case of the other one, experimentally we see both of these, but the probability for both of these to occur are not the same. That is the kind of situation that we see in experiments. For example, if something happens at 100%, some decay, particular decay happens at the rate of say 100 in a particular time interval for a particular sample, and a sample which can be obtained by CP transformation decays to the CP conjugate of that final state, not 100 times, but something like say 90. So, there is an asymmetry between the CP conjugated state and the original state, or the interaction CP, a particular interaction and the CP conjugated interaction. So, this asymmetry, if it is not equal to 0, then we can say that CP is violated, and it is seen that it is not, it is never like 50% or 100%, It is always something like a few percent or less than a few percent that way. We will see now the theoretical developments, and then eventually we will conclude that whatever we have observed, the CP violation as well as parity violation as well as CP violation, whatever we have observed so far can be accommodated in our theoretical framework. So, let us look at the theoretical development again. We did talk about the theory of beta decay, which was proposed by Fermi. So, Fermi's theory was that you consider the invariant amplitude like two currents interacting with each other, nu e u e bar gamma mu v nu bar, and so this is one current which is the electron anti-neutrino current, and the other one is neutron proton, neutron going into proton. So, that is u p bar gamma mu u n. This cannot have parity violation, it's because it is a current vector current interaction. To introduce parity violation, one can look at the interaction in a similar fashion with a slight change. The current is now u e bar gamma mu 1 minus gamma 5 by 2 v nu bar u p bar gamma mu 1 minus gamma 5 by 2 u n. So, Fermi's theory is not, it is modified, but it is not modified drastically. So, instead of a vector current interaction, now we have a mixture of a vector and an axial vector current. So, let me write down one of these currents, say the J E nu electron neutrino current as u e bar gamma mu 1 minus gamma 5 by 2 v nu bar. This can be written as 1 over 2 u e bar gamma mu v nu bar minus u e bar, or 1 over 2 into u e bar gamma mu gamma 5 v nu bar. First one is a vector current, second one is an axial vector current. So, there is a vector minus axial vector, okay. We call it V mu A mu. So, this basically a V minus A structure, the V minus A structure of the current accommodates parity violation. How? Because under parity V will transform in a slightly different way compared to A mu. So, there will not be any particular way to parity transformation property for V minus A. So, that indirectly this theoretical structure will, when you compute the cross section or the decay probabilities, you will see that this will lead to violation of parity, that this particular structure and the parity conjugated structure will not give the same decay probability or transition amplitude. P violation on the other hand requires slightly more involved analysis. We will come to that somewhat later. Now, let us look at the weak interaction further. N going to P, but we know N has one d quark, another d quark and another u quark, and proton has one u quark, another d quark, a d quark and another u quark. So, one can at the quark level think about a d quark converting into a u quark and an electron and anti-neutrino are created. We want to understand it in a way similar to the case of electromagnetic interaction that we had considered, meaning we want to actually connect these 2 points by some propagator, something taking this information from this conversion of the d quark to u quark. That information goes to the pair created and then that is connecting the electron neutrino current. This is again thought of as if happening through the exchange of something, propagation of something similar to the photon propagation in the case of electromagnetic interaction. We denote this by W minus, W for some weak particle or weak boson. Why boson? Because it turns out that this is a vector particle which has spin 1. So, spin 1 integer spin boson. It is similar to the interpretation of photon as the quantum or the representation of the electromagnetic field. Here we consider W particle as the representation as the quantum picture of the weak field. So, W is a particle when you get which is the quantized form of the weak field and we call this W. This need to have a charge because electric charge is changed when you convert a d quark to a u quark. So, to start with, d quark has minus 1 by 3 electric charge, is converted into at this first vertex here, converted into a u quark with 2 by 3 electric charge plus a W boson with minus 1 electric charge. Sum it up, you will see that right hand side has minus 1 plus 2 by 3. So, this is 1 by 3 which is equal to minus 1 by 3 charge. Similarly, when W goes to electron and antineutrino does not have any charge, W has minus charge bringing into that vertex which is taken away by the electron. So, same thing. Okay. So, that is W minus going into E minus plus antineutrino. So, this is roughly the kind of split of this process. There are 2 currents associated with this, one associated with the conversion of D to U and production of W, and this W is then decays to E minus and nu bar. So, W minus is the weak gauge boson. We can look at other processes. It is possible to have a beta plus decay also, which is essentially P going to N plus positron plus neutrino, and this can be thought of as conversion of a U quark into a D quark plus electron plus a positron plus antineutrino. So, this picturized as U quark into D quark with the W plus now, because U has a charge 2 by 3 go into D with charge minus 1 by 3 plus W plus 1. So, that charges are added up properly correctly. This will go into positron. When a positron goes out, we put the arrow in the opposite direction. So, it is E plus and nu E. So, positron takes away the charge which is the W plus, brings to that second vertex here. So, W plus goes to E plus plus nu E. So, we have another gauge boson W plus. So, weak, there are two weak gauge bosons now, W plus and W minus. It turns out that one is the antiparticle of the other. Then you will see that for the theory to be consistent, when we discuss the theoretical model, it will be clear we need another neutral weak gauge boson. This was in fact a prediction of the theoretical framework, the standard model. We will come to that in a little while when we actually discuss the formal framework. So, we have here W plus W minus and a Z0, 3 weak gauge bosons. Right. One is a neutral gauge boson, the other two are charged. Let us consider some other examples of weak processes. We have been talking about the muon, which is like electron, but massive, more massive. It can decay into electron, an electron type of antineutrino and a muon type of neutrino. In all these, we will consider the lepton number being conserved. Lepton, when we say lepton number, muon type particles will have a lepton number called muon lepton number, which is different from electron type lepton number. Individually, they are conserved. So, let us see lepton number electron type, it is equal to 0 here, 1 here, minus 1 here, 0 here. So, total in the initial and final it is 0. L mu similarly is 1 here, 0 here, 0 here, 1 here. So, theoretically that is why we do not have muon going to E minus nu E bar and nu mu bar. Okay. And similarly, in the beta decay, it is the anti-neutrino which is coming out, not the neutrino. Experimentally, one can actually determine whether one particular thing is an anti-neutrino or a neutrino by, for example, considering its reaction with other particles. For example, the anti-neutrino which is coming out from beta decay will not collide with, will not give a reaction like say for example. So, this is one weak process. Diagrammatically, we can represent this as a muon going into nu mu and emitting a W mu, which will go into electron and electron type antineutrino. Okay. So, as we said, in the case of electromagnetic interactions, we do not mix the type of the particles. So, with muon, only muon type neutrino connect. Similarly, with electron, only the electron type neutrino or antineutrino connect. And there are no the fermion lines are continuous from one end to the other. So, this is one way to understand this, and once you know the rules with this associated with this, like in the case of the QED, we had written down the Feynman rules for QED. Similarly, in the case of weak interactions also, we will write down the Feynman rules. Once you get the Feynman rules, then from the diagram one will be able to compute the or write down the invariant amplitude for this process and subsequently compute the probability for it to happen or the decay width. We can think about other processes which also involve weak interaction. We had seen this process. We had seen this in electromagnetic interaction. There we had written down or drawn the diagram. E plus E minus goes to mu plus mu minus through the exchange of photon represented by a gamma. It can also happen through the exchange of weak gauge bosons. Okay. Same final states, mu minus and mu plus in the final state, same initial state. But the intermediate propagator is now different. It is the Z0 that can carry this information. This is the weak neutral current interaction. The propagator is neutral here, and there is no current, the charge change along the current. Charge remains the same all along the current. Okay. Now, so when we consider E plus E minus going to mu plus mu minus, we should be considering both of this. Indeed, the electromagnetic interaction here dominates compared to the weak interactions, but this statement depends on at what energies the electron and positron are colliding each other. So, many times this becomes very important. For example, the neutral gauge boson Z0 has a mass of 91, around 91 GeV. So, if you tune the energy of the electron and positron center of mass energy to 91 GeV, or it turns out that most of this reaction will go through the exchange of Z0, that there will be a production of Z0 which subsequently decays to mu plus and mu minus. We will try to look at some of these processes later, but here we will just try to indicate that along with the electromagnetic interaction in many of these reactions, we will have to also consider the weak interactions. In fact, the neutral gauge boson and the neutral currents like what we have just now written down currents were discovered by the framework of standard model, which we will come to later, and it was subsequently discovered, and that was a big triumph of the model and gave us a lot of confidence in our analysis. There are also other processes like E plus E minus going to two neutrinos a neutrino and an antineutrino of this type. There is no way that this can go through using electromagnetic interaction, in electromagnetic interactions. But in weak interaction, it is possible to have production of Z boson or exchange of Z boson between nu E and nu E bar. Well, rather than exchange, here one can think about production of Z0 and decaying into, which decays to nu nu. Similarly, E plus E minus going to nu plus nu minus, mu plus mu minus through photon can also be thought of as annihilation of electron and positron and creation of a photon, which then pair creates a mu and mu minus and mu plus. Okay. So, this is possible, but as I said, it is not possible to have E minus E plus annihilating to a photon and pair creating a neutrino and antineutrino. This is because photons do not interact with neutral fermions, neutral particles. Photons only interact only with charged particles, at least directly like this. We will see that when we consider the higher order perturbation, there are corrections to this statement. Photons can interact with neutral particles through higher order processes, higher order perturbation process. This is not allowed. Okay. Incidentally, this can also go to the same initial state electron and positron can also go to mu type neutrino and mu type antineutrino. Without being in conflict with any of those lepton number conservation. Okay. So, because it is Z0 which is coupling to any type of neutrinos, but again you cannot have nu E and nu mu bar together. It is either nu E nu E bar or nu mu bar or even nu tau bar. Okay. We will stop our discussion here and then further go on with our discussion on the weak interactions in the next class.